If you're waiting to raise your hand to control smart glasses, you're already too slow. Break time equals 0. 6 is slash because 4 sensors on your wrist read the twitch before your finger even moves. They read intent, not motion. Smart glasses have a problem nobody solved cleanly. You can't talk to them on a train. You can't pull out a phone every time. That defeats the point. So how do you control a screen floating in your vision without looking like you're casting a spell? The answer is a wristband that turns tiny hand gestures into commands. Commands nobody around you can even see. Start with the signal itself. Every time a muscle moves, it doesn't just move, it fires. Your brain sends a tiny burst of electricity down a nerve. That electrical pulse is what tells the muscle to contract. Scientists call this electrical muscle activity EMG, short for electromyography. Here's the part that matters. That electrical command arrives at the muscle before the muscle has finished contracting, before your finger has visibly moved at all. The gap is small, a matter of tens of milliseconds, but it's real. The order is fixed, intent then electricity then motion. Think about what happens when you decide to pinch 2 fingers together. The decision starts in your brain. A signal travels down the nerves in your arm. It reaches the forearm, and this surprises people. The muscles that move your fingers mostly live in your forearm, not your hand. Long tendons run from those forearm muscles all the way down to your fingertips, like cables pulling puppets. The forearm muscle fires first, then the tendon pulls, then the finger moves. So the electricity is always a step ahead of the motion. That's the whole trick this wristband is built on. It doesn't watch your hand. It listens to the electrical order your muscles have already received. Catch the signal early enough and you know what the hand is about to do. So how do you catch electricity from outside the skin? This is where the 4 sensors come in. Each sensor is a small metal contact pad, an electrode pressed flat against the skin of your wrist. It doesn't stick anything in. It doesn't break the skin. It just sits there and reads. What is it reading? The firing muscle underneath creates a tiny voltage on the surface of your skin. And when I say tiny, I mean tiny. We're talking microvolts, roughly a millionth of a volt. Your skin acts like a faint window onto the electrical storm happening in the muscle below. One sensor could tell you a muscle fired, but it couldn't tell you which one. That's the problem 4 sensors solve. Picture 4 contacts spaced around the wrist. When a muscle fires, the electrode closest to it reads a slightly stronger signal than the ones farther away. Compare the 4 readings against each other, and you can work out roughly where the activity came from. That's how the band tells an index finger twitch apart from a thumb pinch. Different muscles, different distances, different 4-way pattern. This is called surface sEMG. Surface because everything happens on top of the skin. The medical version, the kind used in a clinic, pushes a thin needle into the muscle to read it directly. Sharper signal, but nobody's wearing a needle to check their email. The wristband trades that sharpness for something you can actually put on and forget. But a raw voltage reading is a mess. It's noisy, it wobbles, and it arrives as smooth analog electricity, not clean numbers. So the first thing the band does is clean it up. It amplifies the faint microvolt signal to make it readable, then digitizes it. It chops that wobbling wave into a stream of numbers a computer can work with. Now here's the clever part. Those numbers still don't say pinch or swipe. They're just a jagged pattern. To turn a pattern into a meaning, the band uses a machine learning model. Software trained by showing it the muscle signals of a huge number of people making the same gestures over and over. After enough examples, it learns what an index pinch looks like versus a thumb tap versus a swipe, across all the little differences between one person's wrist and another's. When your band sees a new pattern, the model asks one question: which known gesture does this most resemble? And here's what it spits out. Not a moving cursor, but a single, discrete command. Index pinch equals select. That command, just a tiny packet, is sent wirelessly to the glasses. Select. Done. This is why the movement can be almost nothing. The band isn't tracking how far your finger travels through the air. It's recognizing the firing pattern the instant it starts. The muscle barely has to twitch. Enough to make the pattern, not enough for anyone to see. You could do it with your hand resting in your pocket. Now watch the whole thing run in one motion. Your brain decides, select that menu item. It sends the signal. The signal races down the nerves of your arm and fires a forearm muscle. That firing throws a faint microvolt shadow onto the skin of your wrist. The 4 electrodes read that shadow, each catching it at a slightly different strength. A 4-way pattern. The machine learning model reads the pattern and recognizes it, index pinch. It fires off one command. The glasses receive it and the menu item lights up. Break time equals 0, 6 is slash, and here is the payoff to the whole thing. All of that happened from the electrical order your muscle received, not from your finger reaching a destination. The band read the intent, the command your brain had already sent, before the mechanical motion could finish. That's why it registers before your finger moves. It was never waiting for the movement. It only ever needed the electricity. And because electricity moves at the speed it does, the entire loop. Brain to nerve to muscle to skin to sensor to model to glasses. It finishes in a fraction of a second. To you, it just feels instant. So that's the wristband. 4 sensors, 1 twitch, the electrical order of your muscles decoded into a single command before your hand ever moves. But there's a bigger question sitting right underneath it. That model was trained on other people. How does it learn to read your muscles, specifically? And could it one day read you writing letters in the air with a fingertip? That's where this technology goes next, and it's the video we'll open the box on soon.